Yeah. Those who are online, are you able to hear me?
Yes, sir.
Yes or no?
Yes, sir.
Yes, sir.
Okay. So we'll get started. Right on the next chapter's name, that is ray optics and optical instruments. So what is the name of the chapter? Ray optics and optical instruments. Okay. In that, the first topic that we are going to see is the basic introduction to ray optics. Right. So first we need to understand what is called ray optics and why exactly we are studying these things. Right. So further, so in our day-to-day life, we would have come across the applications of different materials like this. So what is this? It is a plane wave. Similarly, you come across this kind of a device. What is it? It's a concave mirror, which is mainly used for, like I can call it as a shaving mirror, right? You would have seen this in many, yeah. And next is what you have is called as a rear view mirror, which is a convex mirror, right? Next is, so what is this? It is a magnifying glass, or in other terms, you call it as a simple microscope, right? And you have something like this, which is called as a compound microscope, right? And this is a telescope, right? So if you see in the first part, the one that we discussed were related to mirrors. And in the second part, these were related to objects which are used for a specific purpose. So these are all called as optical instruments, right? So when it comes to a day-to-day life application, you have devices like this, which is a projector, right? And you have, let's say, a TV or a monitor, whatever you call it, right? And third, you have lens, right? Camera lens, and you have your mobile phone, right? So the question is, how are all these devices functioning? So the question is, what is the source for all these devices to even function in the first place? The answer is obviously light. But here comes an important question. When you say light, there are different kinds of light we can speak about: infrared, ultraviolet, all those things are also light only. But what light is more specific for all these devices to work? It is the visible light. So from yesterday's concept, we know the fact that, a small correction, from the chapter electromagnetic waves, we know the fact that visible light lies in the wavelength range of 400 nanometer to 700 nanometer. So if you're able to use the light within that particular range and discuss about the different applications of it, then that particular branch is given a name. Let us see what is the name given to it. So the name is, the first thing that we need to answer is, what is optics in the first place? Because the name of the chapter is ray optics, right? So what is optics? From all the examples that we saw till now, we understood the fact that visible light plays an important role in functioning of all those devices, right? So if I have to give a definition to it, then optics can be called as a branch of physics. Can I say it like this? So it is a branch of physics which mainly deals with, it is a branch of physics which mainly deals with the study of nature, production, and propagation of light. I repeat, it is a branch of physics which deals with the study of nature, production, and propagation of light. Is this point clear? Right? The next question is, Can optics be classified only as ray optics, or is there any other branch also available? For that, we will see the classification of optics. So optics is basically classified into two types, where one of the branches is called ray optics and the other branch is called as wave optics. This is point clear? So proceeding, we will see each branch of optics in detail. So first, let's try to understand what exactly ray optics is all about, right? So generally, when you talk about the visible light, it interacts with different kinds of objects and each object has a size associated with it. For example, when light is interacting with mirror, right? Generally, when you take a mirror, mirrors have a finite size associated with them, which will generally be in terms of few centimeter or few meter when we try to observe an object, right? Whereas if you compare it with the wavelength of light, what is the wavelength of visible light? It is in terms of few nanometer. Whereas the object it is interacting with is in terms of few centimeter or meter, which is where high, right? You cannot compare these two values. If at all, the size of the object which we are dealing with. So, if the size of the object with which light interacts, so if the size of the object with which light interacts is large compared to the wavelength of visible light, which is generally between 400 to 700 nanometer, light is generally treated as a ray, and that branch of optics is called as ray optics, or sometimes referred to as geometric optics also. Now the next question is, why are we calling ray optics as geometric optics also? We need to give an explanation. Because if you see most of the derivations and the problems that are associated with respect to the ray diagrams that we draw in this chapter, take the help of a lot of geometrical applications. So we use a lot of geometry for us to analyze the situations that are there in every different scenario that is available. That is why if you see, it is mentioned that we use a lot of geometric tools to solve the problem based on ray optics. Hence, ray optics can also be called as geometric optics. Moving to the next point. Shall I proceed? Moving to the next point, we can observe that when you talk about ray optics of light, right, it concerns itself with the particle nature of light, okay, and is based on the rectilinear propagation of light. What do you mean by rectilinear propagation? Means when the light is traveling in a straight path, right? So it is associated with the rectilinear propagation of light and the loss of reflection and refraction of light. And if you see, the main advantage of ray optics is it helps us understand the formation of images in different kind of optical devices like mirrors and lenses. And you will be able to understand the aberrations of optical images. Aberrations means when all the rays do not meet at a specific point. That is, if there is a small glitch that is occurring in the process where the reflected rays are not meeting, is called as aberrations. So the aberrations of optical images and the working and designing of optical instruments. So these are all the concepts that we can analyze with the help of this branch of optics. Rays will not meet. There will be an error. Is this point clear? Shall I proceed? Right. So next we need to answer the other branch of physics, which is called as, the other branch of optics, which is called as wave optics. So what is wave optics? It is just the counterpart of what we saw in the case of ray optics. In the case of ray optics, the size of the object with which light is interacting is very much large. Whereas in the case of wave optics, it will be comparable. Means the size of the object with which light is interacting will actually be comparable to the wavelength of visible light. Means they will be that small. So whenever light is passing through those kind of devices, light starts exhibiting wave properties. It doesn't exhibit particle property anymore. It starts exhibiting wave properties. And you can say, in this particular context, light is treated as a wave, and the branch of optics can be classified as wave optics, or the other name for wave optics is called as physical optics. So proceeding to the next part. In this context, light is concerned, so it concerns with the wave nature of light and helps us explain the phenomena like interference, diffraction, and polarization of light. I repeat, so it concerns itself with the wave nature of light and helps us explain the different phenomena like interference, diffraction, and polarization of light, about which we will learn in depth in the subsequent chapter, that is chapter 10. As far as this chapter is concerned, we will only treat light like a ray and then solve all the problems. Done? Right. Shall we proceed? Right. So the next concept that we are supposed to see is concept of reflection and application in daily life. Right. So actually the topic is concept of reflection and laws of reflection. Okay. So in the previous context, we saw that these are all the places where reflection is applicable because these are all mirrors. So mirrors exhibit the phenomenon of reflection. So then what objects exhibit the phenomenon of refraction? They are lenses. Or you need to have a medium which is, or you need to have a boundary which is separating two different medium, right? As of now, we will be concerned only about the concept of reflection and the laws that are associated with reflection. So, what are the phenomenon with which they work? Obviously, the answer is reflection of light. Right? So, what is reflection of light, basically? So, how do you define it? If I ask you to give a definition to it, how are we going to define it? So, basically, reflection of light means bouncing back of light when it strikes a smooth and a shiny surface. Why are you not writing that? Mind layer. Previous slide on ஞாபகம் இருக்கா? Ray from wave optic difference. எழுதிருக்கியா? காட்டு. அவ்வளவுதான். So what is reflection? Bouncing back of light when it strikes a smooth and shiny surface. Right. So any reason why we are saying or speaking only about smooth and shiny surfaces? Because when light falls on shapes which are irregular, there will be a possibility of irregular reflection taking place, due to which you cannot apply the concepts of the already known laws of reflection. Okay. So now we'll see what are the laws of reflection. For that, so let us consider a smooth and a shiny surface like this, on which there is a ray which is incident, and the name of this ray is called as incident ray. And the incident ray is hitting the surface at a point. And if I name that point as P, that point is called as the point of incidence. So at the first step, I repeat, in the first step, what we are supposed to do is, at the point of incidence, we need to draw a perpendicular to the surface of reflection, which we call it as normal. And with respect to the normal, what will happen is the incident ray will start getting bounced back on the other side, right? So before that, the angle between the incident ray and the normal is called as the angle of incidence, and this reflected ray will get bounced back in this format, right? And the angle between the reflected ray and the normal is obviously called as angle of reflection, right? Now with this, will we be able to define the laws that are associated with it? Yes. So first, we will give a definition. So I is the angle of incidence and R is the angle of reflection. And what are the two laws of reflection that are associated? Obviously, the first one is incident ray, reflected ray, and the normal all lie in the same plane. And the second law that is associated with it is the angle of incidence is equal to the angle of reflection. Is the point clear? Okay. Shall we proceed? So next is we will see plane mirrors and image formation due to it, right? So you have seen these mirrors, right? Like how the images are formed due to plane mirrors. The most important phenomenon that you can observe, or the most important thing you can observe with respect to a plane mirror is something like this will happen. And what is this called as? So laterally inverted image. So there is a lateral inversion taking place. Just give me a minute. Not sure why it is not working. It's fine. Okay. So image formation due to a plane mirror. Okay. Suppose you take a plane mirror like this, in front of which you have placed an object of height AB. Is that clear? So when you take a ray parallel to the principal axis, then what is the angle of incidence? What is the angle of incidence? It is 0 degrees. Because the incident ray itself is acting like the normal, right? Then what will happen to the ray which is getting reflected? It will retrace its path. Okay, retrace its path. And if I take a ray that is hitting this point, let me call it as P. Then if this angle is theta, and at the point of incidence, what are we supposed to do? You should draw a normal, which is obviously perpendicular to the surface. When you do that, this ray will get reflected back in this format, so that this is also going to be theta. Now, what can you say about the first reflected ray and the second reflected ray? So we are clear that first and second reflected rays do not meet in real time. So what are we supposed to do to them? You extend them in the backward direction so that you get a virtual image which is A dash. So you get a virtual image which is A dash, B dash, right? So from this, what is the important point that we can conclude? That plane mirrors form what kind of image? They form virtual image. And secondly, distance of object from mirror is equal to distance of image from the mirror. So if this distance is u and this distance is v, then we can conclude u is equal to v. And lastly, we know the point that plane mirrors show laterally inverted images. Virtual images are always rectangle. When you say virtual image itself, by default it is a rectangle. Is it clear? Shall I proceed?
Can you scroll up?
Yes. Okay.
Thank you, sir.
So next one is we talk about spherical mirrors. So basically, what are spherical mirrors? If you have a spherical surface, and from that spherical surface, if a part is cut and taken out, so that you take the minor segment into consideration. That is, you take only this part, which is a smaller part, into consideration. Then this kind of a surface, if it is polished at one of the sides, okay, then this will become a spherical mirror. Right? So basically, spherical mirror is a small part that is taken from a reflecting surface, where one of the surfaces is left as it is, and the other side is polished. So what do you mean by polished? It is made opaque. Right? So mirrors basically have opaque surface on one side and transparent surface or reflecting surface on the other side. Clear? So having this in mind, let's see what are the parts of spherical mirrors. So when you take a spherical mirror, basically they can be classified into two types. What are they? One is concave and the second is called as convex. So if you take a part from the spherical surface and if you polish the bulged surface, then it becomes a concave, or it has another name called as converging mirror. Concave mirror or converging mirror. Whereas if you polish the depressed surface and the bulge surface is made as a reflecting surface, you call it as the convex, or you call it as diverging mirror. So when you're talking about the parts of a spherical mirror, parts of a spherical mirror, then you can talk for both concave and convex. Concave and convex. Okay. So if I take a point P on the mirror where this P is the center of mirror surface. So if it is the center of the mirror surface, you call it as pole of the mirror. If it is the center of mirror surface, you call it as pole of the mirror. Similarly, if you take a point C, and if C is the center of sphere from which the mirror is extracted, then it is called as center of curvature. Center of the sphere from which mirror is extracted is called as the center of curvature. Next is an imaginary line joining the pole and center of curvature is called principal axis. An imaginary line joining the pole and the center of curvature is called principal axis. So if I take an imaginary line through the pole and the center of curvature, then you can call this as the principal axis. Is that point clear? Is it clear? Next is distance between P and C is called radius of curvature. So radius of curvature is represented by the symbol capital R. So the distance between the pole and the center is called radius of curvature. Next is, we call a point as principal focus, which is represented by the symbol capital F, for which we need to understand a small concept. If a ray is considered parallel to the principal axis, if a ray is considered parallel to the principal axis, after reflection, it will either meet or appear to meet at a point on the principal axis called as focus. If a ray is considered parallel to the principal axis after reflection, it will either meet or appear to meet at a point on the principal axis called as focus. So the name of the point is called as focus, and it is represented with the symbol capital F. So let us take a ray and observe. So if a ray is considered parallel to the principal axis, I want everybody to observe. At the point of incidence, what are we supposed to do? Draw the normal. So normal for a plane surface is easy. You'll just draw the perpendicular. Whereas for a curved surface, how will you draw the normal? How can tangent and normal be the same? Okay, you will draw a tangent at this point. Then you will draw. That is what I was about to say. Because when you draw a tangent, it is actually in the form of a circle, right? What is the property I've learned in your lower grade? If you draw a line perpendicular to the circle at a given point, it should always pass through the center, right? So simply draw an imaginary line that is joining the center and the point of incidence, where this angle will become the angle of incidence. So according to the laws of reflection, the second law of reflection, what should happen is the ray should start bending, making the same angle I with respect to the normal, and this will be the reflected, right? Similarly, if you consider an other ray through the center of curvature, along the principal axis, okay, along the principal axis, where will it meet, or how will it get reflected? It will retrace its path because the angle of incidence is again 0. Okay. Now these two rays meet at a point on the principal axis, and that point is what is called as F. But if you see the definition, I have clearly given you it meets or appear to meet. So appear to meet in the sense, in the case of a concave mirror, they meet in real time. Whereas in the case of a convex mirror, what will happen is, if this is going to be the incident ray, then the imaginary line joining the center of curvature and the point of incidence will become the normal, so that this angle becomes the angle of incidence, and this will be the reflected ray, and this angle will also be I. Similarly, if you consider another ray at the bottom, for instance, then you can draw another normal in this way, where this angle will be angle of incidence, and this will be the reflected ray, and this will be the angle of reflection, which is the same. So the first reflected ray and the second reflected ray have no chance of meeting at all. So when you try to extend them in the backward direction, they appear to meet at a point on the principal axis, which you call it as focus. Or some books give you like this. It appears as if the rays are coming from focus. That also makes sense. Right? So make a note of this. Clear? Shall we proceed? Now see. The next point is, if I take A, B, and here also if I take AB, the length AB is called aperture of mirror. So length AB is called as the aperture of mirror. Okay. An important point to be noted here is, more aperture gives more brighter image. Means the brightness of an image that is formed is directly proportional to the aperture of the mirror. Brighter means more light is falling at a particular point. So the explanation for this is very simple. If I consider a mirror of this aperture and a greater aperture, okay, if I take the rays coming from infinity, so which one has the more possibility of collecting the rays? Actually, these rays can go and hit the screen also. So it is not like the one mirror is kept in front of other. I'm just trying to do a comparative study of the aperture of both the lens. So if you observe, if only the first mirror was existing, then it could have collected maybe 1, 2, 3, 4, 5 rays falling on it. Whereas for the same for the same set of parallel beam of rays, had the second mirror be placed, what would have happened? It could have collected more number of rays. Obviously, all the rays that are going to fall on the mirror will get reflected back and they are going to meet at some point. Means if more light is going to get focused at a particular point, you can say that brighter is the image. Okay. So this is how it works. Is that point clear? Right? So this is about aperture. And yes. So next topic is relation between focal length and radius of curvature. So relation between focal length and radius of curvature of a spherical mirror. So let us consider a concave mirror where you have the center of curvature and you have the focus as well. Now, if I consider a ray parallel to the principal axis, after reflection, where is it going to pass through? It will pass through a point on the focus. Now this is going to be the normal. If this angle is taken to be theta, then how much is this angle? Same theta, right? So if I take P to be the pole and M to be the point of incidence, now, even before we proceed with the derivation, there are two important points that you need to know. First is rays considered are paraxial in nature. So here, what I mean by paraxial is rays which are closer to the principal axis. So rays which are closer to the principal axis are called as paraxial rays. So just to understand, the counterpart of paraxial rays are called as marginal rays. So marginal rays are the rays which are away from the principal axis. Paraxial means you are considering a ray. No? You consider this ray. This ray is closer to the principal axis. Okay. Okay. So here a point to be noted is paraxial rays make very small angles with respect to the normal and other points on the principal axis. A small correction. Very small angles with respect to normal and principal axis. This is after reflection. When rays are going to make small angles, an important point to be observed here is sine of an angle is approximated to tan of an angle is approximated to the angle itself. Sine of an angle is approximated to tan of the angle, which is approximated to the angle itself. So this is one important mathematical conditions. One of the mathematical correction. It is one of the important mathematical conditions that we'll be using throughout this chapter. Right. Second, aperture of the mirror is very small. So aperture of the mirror is very small. From this, what you can notice, when aperture is small, curvature can be assumed to be approximately a straight line. Curvature can be considered to be, or curvature can be assumed to be approximately a straight line. Okay. So due to which, what we can say is if I consider the diagram again, the ray that you have considered is paraxial. See, though I've drawn it at a reasonably good distance. This is only for the understanding, derivation purpose. But you have to imagine that this ray is actually closer to the principal axis. Okay, this is T. If this is theta, this will also be theta, and this point will be focus, this point will be P. No? I told this curvature can be approximated to a straight line so that it looks like perpendicular. Right? Say this angle is theta, then how much is this angle? This angle is also theta. Why? Because they form alternate interior angles. Right? If I take this to be alpha, then what is alpha equal to? Alpha will be equal to 2 theta because exterior angle is equal to sum of opposite interior angles. Okay. So from this, what I can do is, I'll be able to consider two right angle triangles which are MPC, where this line will be theta. I'll be able to consider the triangle M, P, and C. When you join C to M, it makes an angle theta. Similarly, you will be able to consider M, P, and F. When you join F to M, it becomes, or it subtends an angle alpha. Right? So how much is PC? How much is PC? R, and PF is F. Right? So PM and PM are common in both the triangles. Right? So from both the triangles, I can tell one point. So from both the triangles, point that we can conclude is theta and alpha are very small. Theta and alpha are very small. So from the first triangle, if I see what is tan theta, what can I say? Tan theta is equal to PM divided by R. But theta being small, what can it be approximated to? It can be approximated to theta itself, which implies theta will be equal to PM divided by R. And I want you to concentrate again. Whenever you are doing any derivation, you need to apply sign convention to it. Okay. So here, if you see R is on the left of P. So when you see the basic sign convention, any distance considered on the right hand side is positive. Anything considered on the left hand side will be negative. So R is negative. So theta will be equal to PM divided by R. In a similar context, tan alpha will be equal to how much? PM divided by F, which is approximated to alpha itself, which implies alpha is equal to PM divided by minus F. But what is alpha? This is 2 theta. So 2 theta is equal to PM divided by minus F, which is equal to 2 into, what is the value of theta? This PM divided by minus R. PM and PM will get cancelled. Minus and minus are gone, which implies F will be equal to R divided by 2. This is a point which you would have already known, but this is not applicable for all spherical surfaces. It is applicable only for those spherical surfaces where the rays are paraxial and the aperture is small. Only if these two conditions are satisfied, you can say that the focal length will be equal to half of the radius of curvature. And by default, all the problems we are dealing in this chapter follow these two conditions.
So can you scroll up?
Yeah.
Before
Is
this
this
also,
enough?
sir. No, sir. Before this. This, sir. Second problem.
Clear? Okay. So this is all about the relation between f and r by 2. This is the first derivation. And I hope you noted the point that when you're doing the derivation, you need to apply sign convention. And second important point is when you're solving problems also, you need to apply sign convention again. Okay. So with respect to mirrors, there is only one concept that is left out, that is mirror formula. I hope you already know it. 1 by v plus 1 by u is 1 by f. So we'll see the derivation of it in the next class. After that, we can go to the concept of refraction, right? So any other doubt from today's class? Clear? Okay, then we'll wind up.
So can you scroll down?
Scroll down now. Is this okay?
Sir, little up. No, sir. This I have noted before this. Before that triangle. Okay, sir.
You're done?
Yes, sir. Thank you, sir.